So here in this video, we'll start talking about specific heats of gases. A gas have two kinds of specific heats. Specific heat of a gas at constant volume is the amount of heat required to rise unit mole of the temperature's gas by 1 degree centigrade at constant volume. So as at constant volume, I just want to tell you that as volume is kept constant, change in the volume equal to 0. But as for the first law of thermodynamics, dq can be written like du plus dw, whereas dw can be written like pdv. But change in the volume in this case is 0. So du plus p into 0. So that is equal to du itself. That implies Cv can be written 1 by n du by dt. So if you want further, in the place of du, you can write wherever you want n into Cv dt. This is, of course, I am going to use it in the further expression. That's why I have derived this here for you. Now, when two different moles of the gases are mixed with each other, what happens is, what I can say is, I can say total internal energy of the mixer as for the conservation of energy goes is sum of internal energies of the first one plus internal energy of the second one. What I mean to say, total du is internal energy of the first one, second one. In general, whatever may be the number is. So in the place of du, I can write NCV dt means total du means total n. Let n1 is the number of the moles of this first gas, n2 is the second gas, and so on. Then Cv of that mixer, I am calling it like mixer, delta T, all of them are raised to the same temperature. du1 means n1 C1 dt. d2 means n2 Cv2. C1 means I mean to say Cv1 dt, and so on, because this is Cv only. So all dt's can be cancelled further. You got a formula n1 plus n2 and so on, number of the gases when mixed. They have a common Cv mix as N1 C1, N1 Cv1, N2 Cv2, and so on. So if we have to find out Cv of that mix, we can use the formula C1V1, N1 Cv1, that is of the specific heat of the first gas at constant volume, N2 Cv2, and so on by N1 plus N2 and so on. I can use this formula to find the effective specific heat of the gas at constant volume when they were mixed with each other. Now, taking that into consideration, I can solve the problem that is given for you. If 2 moles of gas N1 is given for you, monoatomic. So we need to remember, we need to write this in terms of gammas also, so that it becomes easy for you. What is that? Let me go to the other next part and write something like this. We know relation between Cp and Cv is Cp minus Cv equal to R. And we also know gamma is the ratio of specific heats, that is Cp by Cv. That implies in the place of Cp, I can write gamma into Cv. Then this equation takes a new transformation. In the place of Cp, gamma Cv minus Cv equal to R. Cv is common. This implies in the place of Cv, I can write R by gamma minus 1. Once if you are able to write that, I can get this into a different format. I can use this relation and transform that relation into a altogether a different format. Shall I show you? Yeah. Let us see. Our relation is this. N1 plus N2 and so on and so off. CV of the mix. CV of the mix can be written like what? R CV of the mix can be written as what? As for this, R by gamma of the mix minus 1 can be written as, this is what I have written, this value equal to N1. CV of the first one means R by gamma 1 minus 1. C of the second one is R by gamma 2 minus 1 and so on. So I can cancel these R's and you can get a different format now. So which format you use simply depends on what is the data available for you. You can use any of that, right? So I just want to tell you that there are different formats available for you. You can use any of the formats, either this format or you can use this format. Any format is okay for you, right? Now let's go to the part of the problem that is given for you. Even for going to that part of the problem, we need to know monoatomic gas, diatomic gas. What's the values of their gammas we need to know. So I want to tell you, I want you to remember for a while. As of now, I will tell you in the further videos that how do you get the values of these gammas basing on degrees of freedom. But now, for now, we can say for monoatomic, value of gamma is 5 by 3. For monoatomic, value of the gamma is 5 by 3. For diatomic, value of gamma is 7 by 5. For polyatomic, value of gamma is 4 by 3, though it is not necessary for you right now in this problem. So for a while, assume that these values are given for you. And let's now go to the problem and see what can we do. He has given like this. When these are mixed together, what is the resultant gamma is, right? So let us try to solve the problem. Yes, using this formula. I will use this formula. N1 plus N2. N1 is 2, N2 is 3. So 2 plus 3, only 2. Therefore, I need not write plus and so on. How much I need not write? Gamma of the mix I have to find out. Minus 1 equal to N1 means 2. Gamma 1 means it is monoatomic. Value of the gamma for the monoatomic is 5 by 3 minus 1. N2 is 3. It is diatomic. So gamma of the diatomic is 7 by 5 minus 1. That's it. There is only two gases here. That implies 5 by gamma of the mix minus 1 is 2 by, this is 5 minus 3. That is 2 by 3 plus 3. This is 7 minus 5. That is 2 by 5. Right, so this value is 6 by 2 plus 15 by 2, that is 21 by 2. So 5 by gamma of the mix minus 1 is 21 by 2. When you cross multiply 10 equal to 10 by 21 equal to gamma of the mix minus 1. That implies gamma of the mix is 10 by 21 plus 1. Minus 1 on this side becomes a plus 1. That is 10 plus 21, 31 by 21. That's what you are asked to find out. What is the gamma of that mixture is. You are able to found it. Then what is the resultant ratio of specific heats? We have found it as 31 by 32. So this is found basing on one basic principle that total internal energy is constant, and that is further simplified, modified, written in different format. This is all just mathematics, right? Only thing that I want you to understand is how do you do it mathematically. Go through this, understand this. If you have any concerns, you can just comment in the bottom. Therefore, I will be able to respond to that. Thank you for watching.